Thank you for joining me today. In this video, I will go through how to calculate the average, normal, and shear strains. Previously, we covered what is the meaning of strain. Strain is the amount of deformation. So we are talking about deformation, new deformation relative to the original deformation. So strain is the amount of deformation experienced by the body in the direction of force applied divided by the initial dimensions of the body. Initial dimensions of the body. So we have new deformation relative to the original dimensions. We have two types of strains. We have normal strain denoted by epsilon, and we have shear strain denoted by gamma. If the applied stress is normal stress, that means the corresponding strain will be normal strain. So the normal strain occurs when the elongation of an object is in response to a normal stress. So if you have a normal stress sigma, tensile stress, compressive stress, but it's normal stress perpendicular to the cross section. That means the corresponding deformation or elongation will cause a normal strain. The normal strain is denoted by epsilon. A positive value of strain means tensile strain, and the negative value will be compressive strain. That makes sense? If you have shear stress, if we have shear stress tau, that means the corresponding strain will be shear strain. So shear strain is the deformation of an object caused by shear stress. Deformation not only cause line segments to elongate or contract, but also we have a change of direction. Shear strain is denoted by gamma. So from this slide and in the previous videos, we covered the meaning of strain, and we have two types of strains, normal strain and shear strain. Let's start first with the first type of strain, which is called normal strain. Normal strain occurs when the elongation of an object is in response to normal stress. If we have normal stress, we will have normal strain, epsilon. Perpendicular to the surface, perpendicular to the cross section. Normal strain is denoted by the epsilon, the Greek letter epsilon. A positive value represents tensile strain, negative value represents compressive strain. How to calculate the normal strain? Keep in your mind, strain in general is the elongation or the deformation relative to the original dimension. So if we have a member under the effect of tension force, this member will elongate by a value delta L. If you divide this delta L, the new elongation, the new stretch in this member by the original length L naught, you can get strain. So epsilon, the normal strain, equal delta L divided by L naught. Delta L represents the elongation or contraction. If we have a compressive force pushing this member with original length L naught, this member will be contracted by a value delta L. If you divided this contraction delta L by the original length L naught, you can get also the normal strain. So delta represents the elongation or contraction in the member. L naught is the original length of the member before applying any force. Before applying any force, the member has an original length. Epsilon represents the average normal strain, and this normal strain can be tensile strain if the applied force is tension force, or if the applied stress is tensile stress. And this strain can be compressive strain if the applied force is compression force, or the applied stress is compressive stress. Tensile strain means positive, compressive strain means negative. So keep in your mind the new deformation, elongation, or contraction divided by the original length of the member. We have an example here to figure out how to calculate the normal stress. We have a steel rod. Looks like this steel rod. Looks like this one. This steel rod has an original length. So the length of this rod equal 15 inch. And the diameter of this rod, the diameter is 2 inch. This rod is subjected to an axial tension force. We have a force here pulling the rod or applying tension 20 kip. 20 kip. And this tension force or this axial tension force caused axial elongation of 0.5 inch. So this member stretched, elongated by delta L equal 0.5 inch. What are the average normal stress and strain? So previously we covered that the normal stress equal the applied force divided by the area of the cross section. Is it true? So the applied force on this member is 20 kip. I'm gonna multiply it by 1000 to be in pound. And the cross section is a circle with a diameter equal 2 inch. So the area will be pi divided 4 times 2 inch square. Then I can figure out the average normal stress. It will be 20,000 divided by divide 4 times 2 square. The stress will be 6369.4 psi or pound per square inch. psi. Normal strain equal the elongation on the member divided by the original length of the member. Elongation due to the applied axial force, tension force equal 0.5 inch. And the original length of this rod, steel rod, is 15 inch. If you divided 0.5 by 15, you can get the value equal 0.0333, and the strain is dimensionless. What you mean by dimensionless? We don't have unit because this one in inch and this one in inch. If you divided this number by this number, that means the normal strain will be dimensionless. And this one will be positive, or you can say it's a tensile strain. And because this one is positive, because it's a tensile stress, because the applied force is tension force. That makes sense? So we covered how to figure out the normal stress, and we covered how to figure out the normal strain. The second type of strain, which is called shear strain is measured as the displacement of the surface that is in the direction contact with the applied shear stress from its original position. So most of the time, we have this element with right angle corners. If we apply shear stress, looks like this, looks like this, looks like this, looks like this, the shear stress is parallel to the surface. So we should expect deformation for this rectangle to be something like this. Maybe something like this. So this angle originally was right angle, but right now it will be acute angle. So we have this little deformation in the angle. That makes sense? So this little deformation will be represented by phi, and this phi equal the, in this right angle triangle, equal the opposite divided by the adjacent inverse tan. If you convert this value to radian, this value phi will represent the value of shear strain. That makes sense? So keep in your mind the original angle was a value. After deformation, we have distortion. We have a change in the angle. How much is this change? This change will be measured in degree first, then by inverse tan, the opposite divided by the adjacent, then we convert it to radian. That means this value will represent the shear strain. That makes sense? So we have an example here. So due to the loading, we have applied shear stress. The plate is deformed into the dashed shape shown. So the original shape was rectangle with right angle corners, but after applying the shear stress, we have deformation with the dashed line. Determine the average shear strain gamma in the plate at corner A. So keep in your mind, the original angle was right angle, but after deformation, we have this change. How much is this angle phi? I can say this angle will be inside this right angle triangle. That makes sense? So we need to figure out what is the value of this angle phi. Phi equal inverse tan, the opposite, this value. I think this value will be the same of this value 3 millimeter. And the height, which is this one, will not be 250, but it will be, this height will be 250 minus this change in the height, which is 2 millimeter. That makes sense? So it will be 248. This one in millimeter, this one in millimeter. Then I can figure out the angle phi. So inverse tan 3 divided by 248, it will be 0.69 degree. I will convert it to radian. So 0.69 times by divided by 180 to convert it to radian. Times by divided by 180 equal 0.0121 radian. And with this will be the value of the shear strain at corner A. I forget to mention here, this tan, inverse tan, opposite divided by adjacent, this one in radian, this one in degree. To convert it to radian, I have to multiply it by pi divided by 180. That makes sense? So in this example, one more time, the change of the angle at corner A represented the shear strain. So I'm gonna figure out this angle, how much in radian. So I will need to include this angle inside right angle triangle. So I can set up a right angle triangle like this one. So we have opposite, we have adjacent, the opposite equal 3, the adjacent equal 250 minus 2, which is 248. Once you get the value of the angle by inverse tan, it's in degree, convert it to radian by multiplying it by pi divided by 180, you can get the value of the angle, the change of the angle in radian. We have another example here. We have rectangular plate is subjected to the deformation shown by dashed line. Determine the average shear strain gamma of the plate at corner A. At corner A, the original angle was right angle, like this. But after deformation, we found this line and this line. So the value of the change of the angle, this one, phi 1, and this one, phi 2. So I can say gamma at A, which is the shear strain at A, equal phi 1 plus phi 2. That makes sense? In the previous value, in the previous example, at this corner A, the original angle was right angle, but after deformation, we have a change here in this line. That's it. So the change of the angle was this value of phi. But in this example, the original angle was right angle, but we have deformation in this side and this side. So we have change of the angle phi 1 and phi 2. Let's start to figure out the value of phi 1. Phi 1 equal inverse tan, the opposite divided by the adjacent. So I will put this angle phi 1 inside this right angle triangle. So I can say opposite equal 2 millimeter and the adjacent equal 300. So the angle, so I have inverse tan 2 divided by 300 equal 0.381 degree. So I will convert it to radian time by divided by 180 equal 0.00666 radian. So I included phi 1 inside this right angle triangle, which is very little. So the opposite will be 2 and the adjacent will be 300. In the second angle, phi 2, I'm going to include it in another right angle triangle. So phi 2 equal inverse tan. The opposite in this right angle triangle will be 3 millimeter divided by the adjacent will be 400. So the value of the angle in degree will be inverse tan 3 divided 400 equal 0.429 degree. I'm gonna convert it to radian. It will be 0.00749. Let me check the first one. I think I missed something. Inverse tan 2 divided by 300. Yes, time by divided by 180. It will be 0.00666. We have 3 O after the decimal number. So the strain, the shear strain at corner A will be the shear strain phi 1 plus phi 2. So the final value will be 0.007412. Let me check it one more time. I'm sorry. No, I'm sorry. Yeah, that looks like I messed it up. We have only 2 decimal number. Sorry. So it will be 0.00666, 0.00749. Sorry, guys. So this one will be point like this. So if you add them together, it will be 0.00666 plus 0.00749. It will be 0.01415. That makes sense. Okay. This is how to figure out the shear strain at any corner. Originally was right angle, but after deformation, we have a change in the angle. Sometimes the change on one side, like this one, sometimes the change in both angles, like this one and this one. We have one more example. This example, the piece of plastic is originally rectangular. Suppose that this length equal 300 millimeter, and B equal 370 millimeter. We need to determine the average shear strain at corners A and D. Where is A? A was here. So let's start with corner A. So corner A originally was right angle. After deformation, this right angle became like this and like this. So if you put the right angle one more time at corner A, so we have this change in the angle phi 1 and this change of the angle phi 2. So if you set up here the original right angle, we will have two change of the angle phi 1 and phi 2. Let's start with phi 1 equal inverse tan, the opposite divided by high adjacent in right angle triangle. So I can set up this right angle triangle. How much is this one? I think it will be 2. How did you know it's a 2? This one is 5. This one is 3. So the difference between 5 and the 3 will give you this one is 2. The height is how much? Let's figure this out. This total height equal 4 plus A, which is 300. So it will be 304. If you subtract this 2 millimeter, so this height only will be 302. One more time. One more time. This corner will have a total height equal 4 millimeter plus A 300. So it will be 304. If you subtract this little height 2 millimeter from 304, it will be 302. So this adjacent in the right angle triangle will be 302. So I can figure out the angle inverse tan 2 divided by 302. I got 0.379 degree. If you convert it to radian, it will be 0.06619. Phi 2 equal inverse tan. So phi 2 will be inside this right angle triangle. Does that make sense? So the opposite, which is this one, will equal 2 millimeter divided by the adjacent will be the total length, which is 370 plus 3 millimeter. It will be 373. You add 370 plus 3 millimeter. So this angle will be 2 divided by 373. Inverse tan first. 2 divided by 373. I got 0.307 degree in radian will be 0.005359 the radian. That means shear strain at corner A will be 0.006619 plus 0.005359. So the value will be 0.0119. That makes sense? This is at corner A. at corner A. What about corner D? Okay, let's repeat it one more time. For corner D, just a reminder, this one is 370, this one is 300. For corner D, originally, this corner was right angle. After deformation, we have a change in this angle, and we have a change in this angle. So we can label it phi 3 and phi 4 at corner D. Phi 3 can be inside this right angle triangle. So the opposite will be 2 millimeter and the adjacent will be 373. So for corner D, the first one will be inverse tan, which is phi 3 equal inverse tan, the opposite 2 divided by 373 plus inverse tan for phi 4, this phi 4 inside this right angle triangle. So the opposite will be 2 millimeter and the adjacent will be 302. So I can find out the value of the strain gamma at D will equal inverse tan 2 divided by 373 plus inverse tan 2 divided by 302. So the total will be 0.686 degree. Then you can convert it to radian. It will be 0.01197. Does that make sense? This is the shear strain at corner A. This is the shear strain at corner B, at corner D. That makes sense? So remember, if you would like to figure out the shear strain at any corner, originally this corner was right angle triangle, but after deformation like this one and this one, we have a change in the angle phi 1 and phi 2. If you add phi 1 plus phi 2, you can get the shear strain at this corner A, for example, and keep in your mind this phi should be in radian.